In this exercise, we write down an expression for the density function of a two-component spliced model, in which it is proportional to a uniform density over the interval from 0 to u, and it is proportional to an exponential density from u2 plus infinity. On top, we need to ensure that the resulting function is a valid continuous function. So our new continuous distribution has its support from 0 to plus infinity. From 0 to u, it will rely on the uniform distribution, and from u to plus infinity, it will rely on an exponential. Now, first component is a uniformly distributed random variable, in general on the interval AB. Now we know that the probability density function is equal to 1 over b minus a for x in between a and b. And the cumulative distribution function is equal to 0 for x strictly smaller than a, is equal to x minus a divided by b minus a for x in between a and b, and is 1 for x strictly larger than b. Our second component is an exponentially distributed random variable with parameter theta, and then we know that the probability density function is equal to the exponential of minus x divided by theta, and the cumulative distribution function is equal to 1 minus the exponential of minus x divided by theta, where x is defined in the interval from 0 to plus infinity. Now the two-component spliced model has a density function f, which is defined as a weight, let's say alpha 1 times the first density function, but conditional on the fact that z takes on values in the interval from 0 to u, so z is strictly smaller than u. In the second component, we have a weight, let's say alpha 2. We use the second density function, but now restricted to the fact that z needs to be within the interval between u and plus infinity, so z needs to be larger than u. So for the first component, we consider z in between 0 and u, and for the second component, we consider z in between u and plus infinity. Now, in order for this to be a valid distribution function, alpha 1 and alpha 2 are defined in such a way that the sum is equal to 1. So first component is uniformly distributed on the interval from 0 to u. As we saw before, we take a equal to 0 and b equal to u. Then our density function, f1, is equal to 1 over u minus 0, which is equal to 1 over u. Now, under the first component, our spliced distributed random variable is a uniform distributed random variable, so the probability that z is smaller than u is then equal to u minus 0 divided by u minus 0, which is just equal to 1, which means that our first component, which was equal to alpha 1 times our density function divided by the probability that z takes values within the interval between 0 and u is equal to 1 over u times alpha 1. So for the second component, we consider an exponentially distributed random variable with parameter theta. And then our density function, as we saw before, was equal to the exponent of minus z divided by theta divided by theta. And then the probability under the second component that z is strictly larger than u, so takes values within the interval between u and plus infinity, is equal to 1 minus the probability under the second component that z takes values smaller than u, which is equal to 1 minus the exponent of minus u divided by theta. This means that our second component, which was equal to alpha 2 times the second density, conditional on the fact that z takes values within the interval from u to plus infinity, is equal to alpha 2 times the exponent of minus z divided by theta divided by the exponent of minus u divided by theta times theta, which is equal to alpha 2 times 1 over theta times the exponent of minus z divided by theta times the exponent of u divided by theta. If we combine both components, we get the following expression for the density function of our two-component spliced model. Now, in order to ensure continuity, we need to have that our first component evaluated at u is equal to our second component evaluated at u. So here we see that this is equal to 1. So we need to have that alpha 1 is equal to alpha 2 times u divided by theta. Moreover, we also need that alpha 1 plus alpha 2 is equal to 1. From this, we see that alpha 1 is equal to u divided by theta times 1 minus alpha 1, such that alpha 1 is equal to u divided by theta divided by 1 plus u over theta, which is equal to u divided by theta plus u. From this we then see that alpha 2 is equal to theta divided by theta plus u. As a final result, we get the following density function for a two-component spliced model where the uniform density is combined with the exponential density. And this concludes the exercise.